In terms of principles of operation, there is really no difference between a motor or a generator. The main difference, obviously, is converting mechanical energy to electrical, electrical to mechanical. Any electrical machine can operate as a motor or as a generator. In practice, however, life is a little bit more complicated than that. You don't just build a machine and then decide afterwards what to use it for. You design it specifically to operate as a motor or as a generator, but these are secondary reasons for that, constructional reasons and special requirements. The low temperature superconductivity has been enormously successful in many applications, but rather interestingly, not so much in power applications, for various reasons, mainly to do with reliability and high cost. The high temperature superconductivity, on the other hand, seems to have removed many of the restrictions I just mentioned and carries a lot of promise for this type of application. There are many types of electrical machines. In fact, the most popular type of the machine, probably about over 70% of the market, will be dominated by what is known as induction motors. But there are applications, especially for very large machines, where different types are used, called as synchronous machines. These are the machines which will be used in power stations as generators and in industry as large industrial motor drives. And it is therefore these types of machines which, in terms of large power applications, would be of most interest to anyone.
I think the idea to put together everything in a ship, to have an all-electric ship, using, of course, superconducting devices, is really a very fruitful idea. Power level is, I think, a little bit higher than has been achieved so far, so much work should be done in that respect. But that is a stepwise process.
HTS technology in large power station generators is particularly aimed at improving efficiency. Thanks to the size of units, ranging from 100 to 900 megawatts, a substantial amount of primary energy can be saved, and thus costs. At the same time, these improvements at the source of power generation considerably reduce emissions to the environment.
Well, the torque on an electric motor is normally calculated by the product of the field and the current in the rotating rotor. And of course this is perfectly legitimate. But it's interesting to look at the maximum that we might be able to get from a superconducting material. What are the material limitations? And the answer is that every superconducting motor is dragged round because of the forces between the flux lines and the pinning centers. And therefore the maximum force you can get is BJC per unit volume. We plot the BJC curve for IBCO, or a typical superconductor, but this shows IBCO. And you can see that the maximum of BJC occurs at about 2 Tesla. So this tells us firstly what the maximum torque per unit volume is we might expect. But secondly, the field we have to operate at to reach it. And that's not very easy to reach 2 Tesla in a motor because we don't have the advantage of iron. We need to try to produce this sort of field. However, the benefits of operating at this level are orders of magnitude, and so we don't need to get anywhere near this in order to get big improvements in motor performance. We could improve motors greatly if we could shift the maximum down to, say, 1 Tesla, but keep the maximum value the same, and this is a job for the material scientists. It means that ideally, if you can get the peak lower down, then it's much easier to make a motor out of it.
The electric loading essentially is limited by the current density in the wires, and the magnetic loading is given by saturation flux density of magnetic components. In the case of high temperature superconductivity, there is a possibility of increasing at least one or possibly even both of them. Certainly the electric loading can be increased significantly because the current densities which may be achieved in such superconductors.
From the point of view of practical applications is the critical current density. One employs superconductors in devices and machines because of this possibility of current densities some 10 to 100 times higher than would be possible with conventional non-superconducting materials.
Tapes are made out of the brittle ceramic material in an elaborate high-tech process. In the superconducting state, these tapes are capable of carrying 30 times more current density than copper. This superconductor can be operated with a current of 100 amperes. For comparison, a copper conductor would need this cross-section. For use in electric machines, the tapes are processed into flat racetrack coils, which are assembled into rotor windings of the superconducting synchronous machine. This setup enables considerably stronger magnetic fields in the machine's interior. Simultaneously, it's possible to manufacture the stator with less iron, thus accommodating more power-boosting windings.
In terms of removing the restriction on magnetic loading, it's mainly to do with the fact that we may actually not need certain magnetic parts in the device. Therefore, inevitably, these parts will not get saturated because they don't have any magnetic properties. TS tapes have anisotropic properties. If the field is in the perpendicular direction to the broad face of the tape, then the critical field is much lower. This is a challenge, this is a problem, because the field in the machine will go where it wants to go. So the challenge for the designers is to force it to go in the direction which we want it to go. And that gives rise to a rather clever idea of using so-called flux diverters. This has been used in transformers and generators as well. The flux diverters simply force the field to go in a particular direction, and this is our preferred direction, which is parallel to the broad face of the tape.
The principal components of a synchronous machine with a superconducting rotor winding are the air gap stator winding, the rotating cryostat, a rotating thermos flask that envelops and thermally insulates the superconducting part of the rotor, the pole core, made of a special steel usable at low temperatures, which carries the rotor winding, the superconducting rotor winding, made up of individual racetrack coils, and the torque transmission element that isolates the cold core from the shaft. A self-regulating cooling system is developed to cool the rotor to the operating temperature of about -250 degrees Celsius. A commercially available refrigerator cools the condenser. There, the working gas neon condenses and, driven by gravity, then runs through the cooling pipe into the rotor's interior. Here, it evaporates while cooling the rotor. The vapor returns to the condenser, where it is liquefied again. The cooling system is therefore a closed circuit, so the cooling system operates completely passively and requires little maintenance.
It is in fact much easier to build a device to operate at lower temperatures like 20 to 30 Kelvin, because the properties of the tapes are so much better. So the challenge is really to try to stick to the temperature of 78 Kelvin. This makes the design more difficult, but ultimately, if it's built and if it works well, it will be much better than at lower temperatures. So in the equation, for a given power, if you increase electric and/or magnetic loading, then inevitably the volume may be reduced. You can reduce the volume by reducing D or reducing L or a combination of them. So reducing the size of power devices is one of possible advantages of using the technology. The other possible advantage is reducing the losses. Now the losses in some devices are significant. If you take, for example, a large generator in a power station, a typical generator of about 300 MVA may have over 5 megawatts of losses. Now that still makes the device very efficient, but 5 megawatts is an awful lot of losses.
Superconducting machines have clearly lower losses, which is reflected in a significantly higher efficiency. For example, the HTS machine, belonging to the 4 megawatt class, has an efficiency of 98.7%, in comparison with only 97% in the case of a corresponding conventional machine. This means that losses are halved. Every percent of efficiency increase of one single 4 megawatt machine saves the atmosphere about half a ton of CO2 pollution every day. Despite the same power output, superconducting machines are significantly smaller. The volume and weight savings open up wholly new scope for future applications. Their innovative technology makes these machines clearly less susceptible to load fluctuations. Whereas voltage drops of up to 20% are encountered in 100% load switching by a conventional machine, the superconducting machine suffers a voltage drop of only 3%. The overload reserve is up to 7 times the rated power. Therefore, superconducting machines will be advantageous wherever there is a need for small, compact machines or particularly stable performance. What's more, thanks to the improved efficiency, not only the user profits, but also the environment.
And another quite fascinating application might be to use it as an induction heating. Normally we have copper coils with AC current, which induces eddy current losses to the billet.
The efficiency of the process is the ratio between the power dissipated in a workpiece and the overall power consumption. This equation shows that with a workpiece of high electric resistivity and magnetic permeability, such as steel, the efficiency approaches 100%. On the other hand, when heating a non-magnetic workpiece with the resistivity comparable to resistivity of copper in the coil windings, the root term approaches unity and the efficiency is only 50%. A novel and interesting approach to reduce the losses in a coil is to use the superconductors in the coil windings.
But now we have a DC coil made of magnesium diboride, and we can rotate the billet. That way we can heat the billet, and of course we must have motor and the unit which pushes the billet to the system. And the benefit of this kind of system is that conventionally we have an efficiency of induction heating about 50%, and with this concept it can be raised to over 90%. And as we know, in Europe, for example, there are very, very many industrial plants which are using induction heating, for example, to aluminium and copper.